Well, here we are again. Did you miss me?
Every day.
I hope you all had a good break and are all set for more. I'm gonna have to.
You have a slide echo.
How's this?
It's worse.
Worse. Okay. How about now? Where are you? Okay. Yeah. Well, I'm. What I'll be kind of showing. I need to find a way.
I think it's gone now.
What I'm trying is, yeah, that's me. You may notice my alter ego here joining us. That's so that I can I'm trying to use a whiteboard with my iPad. So somehow I can't turn off the sound completely on my iPad, so I'll have to figure that out. Anyway, here we are again. And now when we last met, the focus was on the Java programming language. And by now you're all wizards in Java because you all passed the course. This is a course in discrete event simulation modeling. And as such, the software that we will happen to use is in Java. And so this is not a course in Java. It's, in fact, the focus on programming is not the most important takeaway from this. So at this point, you may be asking yourself, okay, what the heck is discrete event simulation? You're all students in MOVES, and MOVES stands for Modeling Virtual Environments and Simulation. So simulation covers a very broad range of approaches to solving different kinds of problems. The particular one that we will be dealing with is, let's see here. See if I can see. Basically, it won't give me. There we go. Let me try. I'm trying to get my slides up here, and let's. Where are you? I had it all set up, and of course, it stopped working. Okay, so. Okay, can everybody see this okay? No, okay. All right, so this is our first class. First, we're going to go over the logistics, many of which will be similar, some of which are going to be different. I'll give you a rough overview of the course, and then I'm actually going to dive right in to what discrete event simulation is about, at least a starting point, because it's a fairly complex area, and I will try to make it as simple as possible. Actually, the beauties of it is that once you master the basics, you can do all kinds of great things with it. Okay, just in terms of logistics, we're now meeting at a after lunch for the most part. The times that they've given us are Monday through Thursday at this time, and then they've listed the Tuesday lab at 10. At first, at least, the two, I'm going to have the lectures, they're all going to be lectures, because by tomorrow, I will not have covered enough material to really give you any meaningful quote lab. So at least at first, we're going to be having lectures. Even the labs, one of the things that I noticed is that from the last class, a lot of times the lab time was just sort of spent in you kind of doing stuff, and me just kind of just answering some questions. So at least at first, because there's a certain amount of material that needs to be covered in the beginning, what I want to do is have lectures until we reach a point where we can kind of start doing stuff. The meeting ID, we have a new meeting ID. I am using the same ID now for all of the classes. The password is in the email that you should have received. As with last class, I'm going to record the lectures and upload them to YouTube. I don't know if the YouTube thing is legitimate. Just if you don't tell anybody, it's what is that saying about asking forgiveness rather than permission? So I haven't asked anybody for permission about that. So just don't tell anyone. Okay, so when we have labs, I may have to talk at you for a little bit, just to set things up. I'm trying to have the handouts such that they're almost self-contained, so you almost don't need me for that. Okay, so now one of the differences here is that in the programming class, all of the assignments were programs. Here, there are going to be two kinds of assignments. There are going to be written assignments, and by written, they can either be by hand and scanned in and uploaded. When I teach this person to person, you can just kind of write them on a piece of paper and give them to me. Here in this remote environment, there'll be like a Sakai upload type of thing, and you're a little bit familiar with that. So I'll hopefully get those set up correctly. Those written will not involve any computer programming. That's one of the differences. This is a modeling methodology that we're going to be covering here. There will also be computer assignments, and those will be done via GitLab with the same approach as we did with the Java class, only now we're in Moves 3302. So one of the things that I'm going to have you do to start with is to create a Moves 3302 repository and add me as a developer, as you did with the last time. There'll be more forthcoming on that, because we're not going to be diving into programming right away. We're going to be covering the methodology. The exams are going to be in Sakai. Now the reading, instead of a textbook, the textbook is going to be just this humongous PDF file. It's called Discrete Event Simulation Modeling, and it's a PDF file in the downloads section of the Sakai site. Okay, before I get to that, let me go to the Sakai site. So the overview, again, it lists the Zoom meeting ID and the passcode, since you're the only ones who can see that. Yeah, the Zoom app, okay, we're all here, again, uploaded, etc. So what we have are in the resources section has the class slides, handouts, and downloads. And then one of the things I will point out is that the lessons, I'm trying, Sakai keeps changing things up on me. And so the last time I just kind of dumped everything into this one humongous file because I couldn't quite figure out how to do this. Now I've kind of figured out how to divide it up into different sections. So this is basically an overview of the topics that we'll be covering. The first few classes will be an introduction to what discrete event simulation is. And then very quickly, we're going to move on to something called event graph modeling. And we're actually going to spend most of the class delving into how to create and design simulation models using this methodology called event graphs. What are event graphs, you're asking? Well, hold on, we'll get to that. Not today. I think Wednesday is when we'll start talking about what event graphs are. Before we get to event graphs, of course, we need to have some basics about what discrete event stuff is about. Now, kind of in parallel with the event graph modeling, we'll be implementing these models in something called SimKit. SimKit is a Java library which you can use to instantiate and execute these simulation models. The thing about event graphs and their power is that you can create simulation, you can design simulation models using just pencil and paper and no code. That's kind of the good news. The bad news is that even though we can run small simulations by hand, and I'm going to actually make you do that at first, a little bit, mostly just to appreciate the fact that when we run it on the computer, we can actually get some interesting results. So that's why we're going to be implementing them in Java, but we'll be using this extra library called SimKit in order to provide the discrete event capabilities. Now, some additional, excuse me. The last topics, there's something generating random variates. We encountered a little bit of randomness in the Java course. We're going to delve a little bit more deeply into what these random variates are about, because they are essential in creating these discrete event simulation models. One of the most interesting applications of this methodology, which we will get toward the end of the quarter, is using this to model things that move around and detect each other. So that's going to be the interesting, in my view, application of this. Again, your results may vary, as they say. And then finally, something called output analysis, which we're only going to be able to dip our toe in, because that's actually a very, very large subject. And what that's about is creating the models, which is what we're going to spend most of our time on, but then creating a model for its own sake is really more in the realm of art rather than in something which is useful. We get the usefulness out of basically torturing the simulation model and getting it to confess its results. And we'll talk a little bit about that. Okay, so the resources, again, so here, I put the slides for the first 4 classes in. The sense I got was that maybe you were a little frustrated that in the Java class, things were kind of coming out in dribs and drabs, and you wanted a little bit more of a look ahead. I will try to do more of that here in this class, give you more of a sense of what's coming up. But in the, where is it? Here we go. Okay, so there are now 3 areas in addition to the slides. Okay, the handouts right now, the only there are going to be a few additional handouts here. The main one is this PDF file. I encourage you to just sort of download it so you can have it available to you. And then in the downloads, right now, the main one, I would uploaded all of them. Actually, all you need is this last one. This jar file is what the library contains. This doc zip file contains the Java docs for it, and actually the source file for this. SimKit is an open source package, so you can always see what the source code is. For those of you who are Java wizards, and that includes all of you, you're absolutely free to look at the source code. I would not encourage you to necessarily do that, because the source code in SimKit does not give a whole lot of useful information, to be honest. It does its task, and I think it does it fairly well, but looking at the source code, it's there if you want to, but if if not, then no big deal. Anyway, because so lesson, yeah, again, the assignments will be listed here, and they're going to be coming up. There will be two types of assignments again. There will be both written assignments and computer assignments, the tests and quizzes from here. And there's, okay, so, okay, so again, trying to be as user, okay, so let's, all right, now I want to go back to that. Okay, now what, just to put some of this into context, I've been working in this for, since dinosaurs ruled the world. And this is a, in the NPS Dudley Knox Library, if you search for theses that I have advised, you will come up with 171 hits on this, going back to the 1990s, which is when I showed up here. Not all of these use SimKit, but most of them do. Some of these use an earlier version of SimKit. I think if we, let's see, if we filter by some of the more recent ones. So, so here's one that was used in an analysis of a swarm attack, modeling anti-air warfare. This one, depot level maintenance of the LAV, artillery fire projectors from the score. This was a particularly out of the box one. This was modeling the Polaris 2.1 gamma ray imaging radiation detection device. Mission command, storage. What you should take away from this is, first of all, a lot of students have used SimKit in their thesis for creating their models. So that is something which is something absolutely doable and something that you might want to consider. I mean, obviously, I am a little bit biased when it comes to whether that's a good idea or not. I think it is. The other thing is that you may notice the wide range of applicability of these. Just by reading the titles, you can see that there are a wide range of situations where discrete event approach can be used effectively. And not only that, as you're probably aware, there's a fairly constrained timeline in your time here at the Naval Postgraduate School, and you will all be writing a thesis. And as part of MOVES, there's a broad range of possibilities for that thesis, from things involving human systems integration, from virtual environments, and some involving these discrete event simulation approaches, which take a situation and try to find something out about it. In that constrained time, many students before you, at least 170 or so, have taken this approach and successfully created a simulation model and successfully produced some interesting analysis of that model. So this is something which is very, very doable. And it is something which, well, not only is it doable, but it's something you can actually do. Okay, so let's get back to our where were we? Okay, we have to start right at the beginning again, of course. Where were we? Okay. Okay, so I'm going to spend the rest of our time here going over roughly where what we're doing fits in first, and then begin talking about what is a discrete event simulation. Okay, so there are a number of different ways to break down how simulation's used, and one of the first bifurcations has to do with its purpose. Here in MOVES, the main difference is between use of training and that's where many of the virtual environments come in. And analysis is about taking a situation and trying to figure something out about it. That typically does not involve fancy graphics or virtual environments. It involves a more abstract approach, an abstract approach that you'll be tortured with for the rest of this quarter in this class. So analysis is where we're going to be focusing our attention. The next place where simulation models differ is in how they advance time. See, with a simulation, with a dynamic simulation that we're talking about here, if you're in a virtual environment, then we're talking about real time. If we're talking about things like agent-based models or discrete event models, as we do here, there is a simulated time which is almost always faster than real time. And that's important because if we want to find out what a system will be doing over the next 10 years, we can't be running it in real time. Okay, so that almost goes without saying. And so therefore, if we're modeling that, we need to make simulation time run faster. So when we say simulate time and simulation, that refers to simulated time, not actual clock time. There are two main methods of modeling time in simulation. The first is called time step. And what that involves is having a discrete amount of time. And what you do is you basically click the clock and advance it by a certain amount of time, and then do whatever you need to do, and then advance time again. Most, but not all, agent models use this time step approach. However, in discrete event simulation, we use something called the next event approach. And there's also something called a hybrid that tries to combine them. But the point is, we will be using the next event approach. From time to time, you will hear me dissing time step. So if you're used to a time step agent model or a time step combat model or anything like that, then please don't be offended. But in discrete event simulation, we use something called next event, and we'll see what that's about. The other thing to kind of remember, and if you've taken classes over in Glasgow Hall, you probably have heard this statement that all models are wrong. And this is something that's important to understand. Having a model be wrong is not a bad thing. The corollary to that is that some models are useful. So models can be really badly wrong, and models can be wrong in a good way. What is meant by that is that every model is an abstraction of what it's trying to model. In other words, typically you will have an actual situation that you're creating a simulation model for. No matter how much work you put into it, no matter how detailed you get, that model is not going to capture everything in the system you're trying to capture, no matter how much detail you put in. So it's wrong in the sense that it does not capture everything. If you've done the modeling well, then the model captures the essential details for the kind of questions that you're asking of it. Okay, so let's, okay. All right. So that's where discrete event simulation fits in. It is typically used for analysis, meaning that we have a system or a proposed system and we want to find out something about it. And we will be using something called the next event time advance model. So what goes into a discrete event simulation? And one of the reasons why it's, for me, a very attractive methodology is because it's actually quite simple. It just consists of three things, which are actually two things, really: states and events. There are also things called parameters that we'll add in later. That's the third one. Okay, so we're talking about states, events, a thing called the event list, which is how the time advance is actually managed, because it doesn't just happen. It is something that actually has to be made to happen. And we'll talk about the structure of a discrete event simulation model. DES is the abbreviation, and time permitting, we'll have some examples. Okay, so discrete event simulation, we define our model by a collection of states. And those states what is a state? That's something that's going to come into focus. For right now, we're going to leave it a little bit undefined. It's kind of like a snapshot in time of your system. It's something that describes the essential elements of your system. As we work through examples, specific examples, what a state is will hopefully come into focus a little bit more clearly. Now, one of the things that characterize discrete event simulation are its state trajectories are piecewise constant. You know, what's a state trajectory? Does the term state trajectory convey anything to you as intuitively? If I were just use that term, does it kind of bring up anything? Can you picture what that might be?
Is it project the future state of the model?
Kind of, yeah. Basically, it's a little more simple than that. Basically, a state trajectory is just a graph of your state value over time. That's all it is. So the trajectory is the fact that it's over time, and the state part just says that this is how our states change value. Now, the thing about discrete event simulation is that its state trajectories are piecewise constant. We'll talk a little bit more about that. And so therefore, what happens when a state changes value is it happens instantaneously in simulated time. In other words, it jumps from one value to the next. That's obviously unrealistic, because everything that happens in reality takes a certain amount of time, and that's where some of the abstraction comes in. But that's a key element of what this is. Those jumps are what we call events. In other words, what is an event? An event is when a state changes from one value to the next. Now, depending on how much quantum physics you know, and I know like epsilon quantum physics, but I know enough to know that in quantum physics, this is actually a real thing. In quantum physics, there's actually a notion that you instantaneously move from one state to the other. So, but we're not talking quantum physics here. We're talking, we'll be modeling things like waiting lines. We'll be modeling things like inventory systems and things like that, where things happen in real time, but we're going to pretend that they don't. Okay, so again, what is a state? Well, again, a first cut is going to be, give me a set of variables that describe a snapshot of the system. In other words, if we were to stop our system and say, can you describe everything that is relevant in this model, then that would be done by what these states are. Where do these states come from? That's what you, the modeler, are responsible for creating. When you create a discrete event simulation model, one of your tasks is to define what those states are. And we'll see examples of that. So again, a state trajectory, we mentioned this, it's just a graph of the state over time. The discrete event states change instantaneously, so the state trajectories must be piecewise constant. So that means that they can't look like any of these. So for example, if I'm modeling the trajectory of let's say an artillery shell, that might look something like this red one right here. If I'm modeling something like coronavirus cases, we've seen a lot of graphs that look like this blue one. Or it may look like this thing on the right. Notice these are all literally continuous. Those are inadmissible. In a discrete event model, we cannot have a state trajectory that looks like that. All of our state trajectories must look like this. So here's a state value, which I'm graphing over simulated time. And this state changes, it's fixed for a certain amount of time, and then all of a sudden it jumps up to this value in 0 time. It stays there for a while and then jumps back down here. Stays there for a while, then just jumps back down to this value, stays there for a while, jumps up to that value, and then on. Those are that would be the state trajectory for this state. And those places where those jumps occurred, these are what we would define as the events. Okay, so that's why having these piecewise constant state trajectories is a critical element of discrete event simulation, because without that, we can't define where our events are. With that constraint, we can explicitly say our events are going to occur here, 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 and here. And actually, there's going to be an event right here in the initial, as we'll see. So just to dive into this a little more, events are where an interesting thing happens. You know, what's interesting? The only interesting thing in a discrete event model is when a state changes value. In between events, see, in between events, nothing happens. See, from this time, from this event to this event, in this model, if this is the only state for state in this model, between this time and this time, nothing happens. Okay, that's an important observation. Now, the events may schedule other events, and we'll sort of dive into that a lot, because that's going to be a key part of defining our discrete event model. So, for example, one event might be a missile is launched. And that event, launch missile, will typically schedule another event sometime later, missile impacts. Okay, now without worrying about the specifics of the trajectory, if those two are the only interesting things, so if all I care about is when was the missile launched, where and when did it impact, and what effect did it have, what it did in between is I'm not interested in. In other words, I don't care about that parabolic trajectory or whatever its trajectory may be, because I can't explicitly model that in discrete event. But the only things that affect me are the launch and the impact in this particular case. So that's an example of one event scheduling another event. The order of that events occur may not necessarily be the same as the order that they're scheduling in. So, for example, I may launch one missile, which has a long distance to go, and a while later, I may launch another missile that has only a short distance to go. And so that second missile may impact sooner than the one that I launched earlier. So that for the model to be correct, the events have to occur in the order that they actually occur. And we'll see what that's about. How does it do that? With something called the event list, or in the reading, it's called the future event list, or FEL. I've kind of come to, mostly I'll be using the term event list, but future event list is another one that you'll get. So the idea is that these events, and in the implementation, you can think of these events as being objects. The events keep the pending events in a list, actually in a sorted set is in the implementation. And what it does is it inserts the events in order when it's scheduled. The order is the order that they are scheduled to occur. And the key thing is this logic right here, the way that it advances time. And this is that next event methodology. What it does is it says, okay, when is the next scheduled event going to occur? And it's going to jump time from time now until that next event. It'll just jump over everything. Why? Because in between events, nothing happens. Nothing of interest happens. And if nothing's happening, then there's no sense in kind of clicking along like a time step would do when you're going to get the same answer every time. So why not just jump right ahead to the next interesting thing? Then what the event list does is it removes the event. It says, okay, now we're going to process that event. What does it mean to process the event? To process the event means to execute its state transition, which the modeler has defined, and then schedule any additional events, which also the modeler has defined. And you keep doing that. And when it's done with all that, it says, okay, when's the next event? And you repeat that as long as there's another event. When you run out of events, it's like, okay, the universe ends. Nothing more can happen. So starting up, now think of how you might implement this. This is actually implemented using a sorted set in Java, but that's not important. What's important is just that given this logic, if I'm going to keep going as long as the event list is not empty, then I'd better, when I start up, what's on the event list? Well, nothing. So I need at least one initial event. And that's kind of like the main method in Java. It's like in Java, we wrote objects all over the classes, all over the place. But where do you start? You start at the main method. In discrete events, that initial event it's called run for historical reasons. And so every discrete event model is going to have a run event, which is always scheduled to occur at time 0. And so that ensures that the event list is not going to be empty at the start. And so at least we have a fighting chance of it doing something. And then the only thing that distinguishes the run event is the fact that it's put on the event list to begin with. After that, you get processed like any other event. It has a state transition. It schedules other events. Those are the only things that events do. So that brings us to the overall structure of a discrete event model. And there are basically 4 pieces to this. We've mentioned state variables, but there are also value. We want to parameterize our models. And as we delve into this, you'll see why that is something that's very useful. But strictly speaking, a parameter is a variable in the model that never changes during this single run. We'll see examples of that. But a state variable is what does change. And those state variables are what we are interested in. Parameters are what helps make it go. So for example, for our missile, one of the parameters might be its ground speed once it's launched. Other parameters, we're going to be looking a lot at queuing systems. There are parameters like the number of servers that we have in a service operation. Okay, so there are 2 variables, parameters and state variables. Parameters don't change, state variables do. How do state variables change? The term is state transition. So an event is, and again, it's that jump that we saw back here. This is a state transition, which moves the state from this value to that value. And that's what we're identifying as events. So an event is when that state transition occurs. And then the final piece are the scheduling of relationships. Those are the events that schedule other events, such as, you launch the missile, it schedules the impact of the missile. In our queuing models, they might be things like a customer arrives. And when a customer arrives, if there's an available server, that customer can start service. And if not, then they'll wait on the queue. We'll see examples of that. Okay, so this is the hello world of discrete event models, the simplest non-trivial one. And it's called the arrival process. And it's actually a very useful one, but it's really very simple. It has one parameter, one state, and essentially one event beyond, except for the run. So now its parameter, this is something that we can do with parameters, is that many times we'll have sequences of values. In this particular case, what we're modeling is just the arrival of things. Our most common use of this is going to be modeling the arrival of customers to a facility, such as a store, or, well, let's see. You've never, I don't think we've been on campus. We certainly haven't been in, there's a, like in the cafeteria, in the basement of Herman Hall, there's a cafeteria where when we're on campus, we often go for lunch. And when you go to one of those places, then, for example, if you go to the sandwich place, then there's only like, there's a person making the sandwiches. And if they're making a sandwich for someone, then they can't wait on you. Think of the last time you were in a bank. I know it may be a while before we're out of the home, but, or think of a call to support. Have you ever, you make the call, and then what you get is, after a number of different menus, you say, you get, oh, your call is very important to us, and there are people ahead of you. There, all of our service people are busy, but we'll get to you as soon as we can. That's an example of a queue. So the arrival of those calls to that facility would be an example of this. So these inter-arrival times, that's just going to be a sequence of these things. We will typically use that as a sequence of random variables. And we'll see examples of that. But it's technically a parameter because that sequence is kind of given outside of the number, the value. So our state variables, we're just going to count the number of arrivals. All we care about, we're going to sit at this facility and we're going to stand there with a little counter, and every time somebody comes in, we're going to click another one. So now there are two events for this. Now remember, our run event is going to be where we start. And so what it's going to do is its responsibility is to initialize all our state variables. So the run event state transition is going to set the value of n to 0. And I should have specified that in the up here, because that's part of the state. So the run event will set the value of number of n, the number of arrivals, to 0, and then it will schedule the first arrival with a delay of the first t sub a value. So it says the first guy is going to show up at this time from now. And then the second event, or actually really the first real, quote, real event, is I'm going to call arrival. And its state transition is n equals n plus 1. In other words, every time there's an arrival, I have one more that I'm counting. That's the state transition. I mean, rocket science, right? And it will simply schedule the next arrival with a delay of the subsequent t sub a values. In other words, every time this arrival event occurs, it'll grab the next generated value of this t sub a inter-arrival time, and then say, okay, the next guy's going to come that much time later. Okay, so this is a simulation model in every sense of the word. This is a simulation model in every sense of the word. Now, you can't run it on a computer. So maybe you were under the impression that all simulation models must be in code on the computer. And I've now proven that false, because here is one and there is no code anywhere. Now, having said that, to be useful, we're going to have to implement this. And in fact, this is going to be the first one I'm going to have you implement when we get to that. So here's a possible state trajectory for that arrival process. See, so here are different values of t sub a. Now notice that they're all, I just listed them as t sub a here, but you see it starts off at 0, and then at a certain time it's going to, oops, see the t sub a is a time between here and here, and then it jumps from 0 to 1 at the arrival event. And then the next t sub a may be a little bit shorter. And then when that event occurs, it's going to jump up to 2. And that one may be it may spend a little bit longer. How do you know? Well, whatever the next value of t sub a is, and then it jumps up, etc. So the state trajectory for the arrival process is always going to look something like this. It always increases, it never goes back down. Okay, so that's what that is. Now, I'm going to try something here just in the last few minutes, and that is that the reason I need to do something with my doppelganger. Oops, what the heck happened? I lost him. Lost the connection. Darn it. Give me a second here. Darn. Because in modeling these things, it is usually, come on, open on the dialogue, open, come on. Come on. It's infernal contraptions. Come on. Copy. Come on. Can't do it. Well, we may have trouble. All right, I'm going to give it one more try because I have a couple of minutes. Open. Why won't you paste? Paste. Ah, got it. All right. And I'm going to make you a co-host, make me a co-host. All right. So now, oh. Can you see that?
Yeah, we can see a white screen.
Oh. Okay. You see that?
Yep, we can see it.
Okay.
Looks great, sir.
All right, yeah. So because when we meet in person, I like to do a lot of the modeling on the whiteboard rather than death by PowerPoint. There will be a certain amount of PowerPoint, unfortunately. I will try to minimize that. And in fact, what I'm going to, a lot of times, especially when we dive deeply into the modeling, I'll spend some time using the whiteboard to create the model, and then afterwards upload the resulting model in the PowerPoint. So in other words, in some cases they're going to be a different procedure. That is, there will be, instead of having the PowerPoint slides up front, there'll be the whiteboard and then the PowerPoint slides afterwards about what was done. If that makes sense. If I can kind of keep the silly thing up here. Okay, so my iPad keeps crapping out. Anyway, okay, so that's it for today. I will see you here at 10 o'clock tomorrow and also at 1 o'clock. So Tuesdays, you get a double dip. And if there are no further comments, then I will adjourn and we will see you then.
Matt, we can't hear you.
Okay, I see lips moving, but no, I don't hear you.
I think what Matt was trying to say, Arnie, is so we had a class Tuesdays at 11. We no longer have class on Tuesdays at 11. It got moved. So how would you be opposed to doing class on Tuesdays right after, or lab and class pretty much one after the other? Do you have that 11 to 11:50 block available?
Actually, that would work out very nicely for me. In other words, have a double session. Go from 10 until 11:50.
Yeah, as well as we actually have that block open Thursday as well. If you were available Thursday to do 11 to 11:50.
I can do that. So let me just, I better write this down. So Tuesday, it'll be 10 to 11:50, and then Thursday as well, 11 to 11:50. But then Wednesday, it'll be at 1300.
Yeah, that's correct, because we've got class 11 to 12:50 Monday, Wednesdays.
Okay. All right. I will, that I'm fine with that. And I will update things accordingly.
Cool, thank you.
Okay.
As long as everyone else in the cohort agrees, I think
Yep.
most people are on board with that.
Yeah. Thank you, sir.
Okay.